Great, okay. Hi everyone. Excited to tell you all about our work on the verified correctness and security of mbedTLS HMAC-DRBG. This is joint work with Matt Green, Nafat Sangwenson, Leonard Berenger, Adam Petcher, and Andrew Appel. mbedTLS is a widely used real-world implementation of mbedTLS. HMAC-DRBG is a pseudorandom generator that was certified and released by NIST, a government agency in the US. So, why verify pseudorandom generators? The point is, most modern crypto systems rely on high-quality randomness. It is absolutely essential. For example, RSA requires a large amount of entropy in order to generate random big primes to compute a private key. A high-level overview of what a PRG does. It is a box that takes a small amount of high-quality entropy from a source like quantum noise mixed with mouse movements, for example, and stretches that into a large amount of pseudorandomness that is hopefully indistinguishable from true randomness by a bounded adversary. However, if its output is distinguishable or predictable from true randomness, then bad things happen because reducing the entropy of a cryptosystem's PRG is a great and easy way to break the entire cryptosystem. This is something that, for example, the NSA knows well. In the famous case of the backdoored dual EC-DRBG, where the NSA was able to pick a compromised P or Q for the elliptic curve used in this PRG. Another real-world example is the Debian OpenSSL PRG. As this XKCD comic describes, a developer actually commented out some lines that were used to add extra entropy to the seed in order to avoid a compiler warning. And what happened was that by removing the source of system entropy, there are actually only 32,000 sources, or 32,000 choices of value for the seed, which was the process ID, so that let an adversary predict SSH keys for organizations like Spotify and Yandex, and then they were able to compromise them. So secure PRGs are absolutely vital, but it's actually not clear how to ensure this. As the Stilbert comic shows, over here we have a random number generator, but the problem with randomness is that you can never be sure. Some existing methods are, for example, NIST actually has in its specifications some test vectors. So if you put in a certain input, you should get a certain output from your PRG. But obviously, that's not enough to ensure indistinguishability and other properties. Another approach is to use statistical tests, but again, that can only give you a certain degree of assurance. We need better ways to ensure that PRGs are secure. Our work proposes a new paradigm to prove the functional correctness and cryptographic security of PRGs, in our case, a widely used implementation of HMAC-DRBG. For correctness, we use the tool, the verified software toolchain. For security, we use the tool, the foundational crypto framework. So just a summary before I dive into the details, we prove that the output is indistinguishable from random to a computationally bounded adversary subject to some standard crypto assumptions. We performed a typical real ideal indistinguishability proof in the computational model using a hybrid argument on the number of calls to the PRGs, and we did derive a concrete bound on the adversary's advantage. The foundational crypto framework is a COC framework for reasoning about the security of crypto schemes, and you write games or programs in a probabilistic programming language. The verified software toolchain, or VST, is a COC framework for verifying the correctness of C programs. So these may include pointers and mutable state and so on, and it provides a logic to deal with that. Here's an overview of our work and how the components link together. First, we start with the NIST paper specification of HMAC-DRBG. This is a paper, digital document output by a government agency. We transcribe that into a functional specification of HMAC-DRBG. This spec is written in Galena, which is a high-level functional language in the COC proof assistant. Then we state theorems about cryptographic properties of the functional specification, also in COC and FCF, and we prove these properties with FCF. Then we prove, using the verified software toolchain, that the C implementation of HMAC-DRBG in mbedTLS indeed does satisfy its functional specification. It does what it should. And these two proofs compose at the interface to give us a end-to-end security and correctness proof for a real-world DRBG implementation. In fact, you can take this and give it to the ComSort verified compiler and get verified assembly code that really runs. Another advantage of our machine-checked approach is that our proofs are modular because of this well-specified interface. So say you are not happy with the property we proved. You want to also prove that the PRG has another property, like backtracking resistance. You can separately rely on our specification, not interface with anything else, and add it on top of the functional specification. Say you wrote another implementation of HMAC-DRBG, and you want to show that it possesses these properties. All you have to do is rely on our interface, and separately, you can do this correctness proof, and you can have all of these properties flow down for free. Say the C implementation of in mbedTLS evolves, then you can reprove that proof, or you can evolve the specs around it and still get the same modular proof niceness. Now I give an overview of what HMAC-DRBG actually does. What it stands for is Keyed Hash Message Authentication Code Deterministic Random Bit Generator. The typical PRG interface looks like this. So you have some seed, hopefully high entropy. It is passed to an initialization function, which creates an initial state, which is repeatedly transformed by some transformation function, and an output function generates some random bits, which you get. The API consists typically of these four functions: instantiate, generate, which is the most important, reseed, which is to add entropy, and update, which updates the internal state. So typically, a user or adversary might instantiate the PRG, then ask for 10 blocks. Blocks is just a synonym for whatever the output size of the internal PRF is. So it might ask for 10 blocks, and then the PRG will update its own internal state. Then you might ask for 20 blocks, it will generate that, give it to you, it will update its state, and so on. Maybe if you ask for a lot of randomness, it will reseed itself, and so on. So the secret state here consists of K, the secret key, and V, the initialization vector. F is a hash function, which I leave abstract in this presentation, but is HMAC specifically. And random bits in generate are created at a high level like this. So F, the hash function, is keyed with K and given the initialization vector, and that output is the first block of the random output. Then you take that and you plug that back into F again with the same key, and then you take that output, you plug that back into F again with the same key. So visually, what you're doing is you're taking the output and you keep plugging it back in as the input with the same key. That's how the inner loop of the generate function works for HMAC-DRBG. So the entire function, the API looks like you give it a K and a V, generate some blocks, you take the last block of output, and that, along with the same key, goes into the update function, which refreshes the K and the V. Now let's zoom into what this update function actually does. So you give a K and a V, the state, and first it rekeys the PRF. This is important. It uses the same key, and given the V, it rekeys that PRF. And with the new key, it generates a new V, a new component of the internal state, and those are the new internal state. So in use, it looks something like this. You, or the adversary, you want a list of blocks. So first you wanted 3 blocks, then later for another application you want 1 block, then later to initialize another thing you want 2 blocks. So that's the input. And the DRBG, it takes KV and instantiates it. So we assume the output is ideally random to simplify our proof. The output K and V are given to generate using F as the internal PRF, and 3 is an input, says it wants 3 blocks, it outputs 3 blocks, and that continues. So it updates the internal state after generating. Then for the next call, 1 block, generate, update, and so on. And that output down there, those icons indicate random noise or whatever outputs. Those are given to the adversary or you. How does our proof of indistinguishability from random work? Let's dive into that. So first, it relies on a proof of HMAC being a PRF, which in fact we have mechanized earlier in our Usenix Security 2015 paper. And that HMAC proof itself relies on standard assumptions about SHA being a good hash function and being collision resistant. So this section is going to talk about that first green arrow, the proof of indistinguishability. Our proof is actually structurally similar to an existing proof by Hiroshi 2008. So Hiroshi did this proof entirely on paper. We do arrive at similar bounds and need to do it first. However, their proof omits several components. They don't do it fully, and it is not tied to any working real-world HMAC-DRBG implementation. The first step of our proof is to combine the generate and update functions. This is a program equivalence proof. So this is actually an artifact of the way NIST chose to specify this DRBG, because, recall, it is rekeyed halfway through update. It makes it messy for us to define hybrids for each call of the PRG. We need to define the calls in a nicer way. So these dotted boxes denote the lifetimes of the various keys. The first key has a lifetime through the first call to generate, then the first half of the update call. Then it's rekeyed. Then the second key, K1, has a lifetime through the second half of update, through all of the next generate call, and then through the first half of the next update call. And the third key, K2, has a similar lifetime. So what we do is we just combine those dotted boxes down and squish them into these new functions we call genUpdate prime for just the first call, and then genUpdate for all subsequent calls. And this allows us to nicely define hybrids for each time the PRF is rekeyed on each call. Now I define our real-world and ideal-world hybrids. So the real-world hybrid is simply the PRG as it is used. Nothing is different. It's the same PRG you know and love. And the ideal-world hybrid, notice the difference. We're replacing every single time a PRF is called inside HMAC-DRBG. Every single time we take that input and then we sample an ideally random output. And that is whatever it outputs. And it is fairly clear that that will produce output that is actually ideally random. So the real world and ideal world games use the hybrid definitions, simply adding adversaries that can give it some input and then examine the output and have to output a guess about whether the internals in that red box were the PRF or ideal randomness. Now I discuss how we bridge the real world and ideal world definitions with intermediate hybrids. So real world left, ideal world right. We start with the real world hybrid, and what we do is we examine just the first call, and we replace the PRF used there with a random function. So I will review what that is in a second. But so every single call to the PRF in the first call to genUpdate prime is going to be sent to a random function, which is going to sample its output, ideally at random. Then the next hybrid for the first call is to sample every single output truly randomly, so throughout the random function and actually sample everything ideally at random. And then we repeat this process for each call to the PRG. So second call, replace PRF with random function, then replace with ideal randomness. Do that again for the third call, and then we end at the ideal world hybrid. So the games are close due to a standard application of the hybrid argument. A quick review, the hybrid argument is essentially the triangle inequality, but repeatedly applied. And in this case, the points are distributions, and the distance between distributions is going to be bounded by the distance to some intermediate point, which is an intermediate distribution, which is a hybrid. So visually, the main hybrids are going to be all PRFs, H0, and then all ideal randomness, H4, and then the intermediate ones, we just replace each call with ideal randomness. Now let's go over each individual hybrid and what the advantage is there. How do you distinguish a pseudorandom function from a random function? So that's going to be bounding the chance of distinguishing between these two hybrids. Well, recall HMAC is a pseudorandom function, but what is a random function again? So here we understand the random function as a lookup table. So you give it some bit vector, that's what the black and white glyph denotes, and it takes that, it stores it or caches it in its lookup table, then it samples a random output, stores that, and then gives that to you. And if you happen to query it again with the same input, it's going to look up the output without resampling it and give you the same thing. A pseudorandom function is defined in relation to this definition. It is defined in terms of a PRF advantage. which is essentially the adversary has to play a game to find the PRF or find the fake. So it's given these two oracles or like wrapped gift boxes it can't look inside, and it can ask each one a bunch of queries and examine the answers as much as it wants, well, boundedly, and then it has to output a guess as to what box the random function or the PRF was actually in. So pseudorandom function defined by hard to distinguish from random function. Now, how do you distinguish a random function from true randomness as it is used in HMAC-DRBG? So that is going to be bounding the chance of distinguishing between these two hybrids. Note that intuitively, a random function is only distinguishable from true randomness if you call the function on the same input twice, because then it will output the same thing twice, and that is very unlikely to happen with true randomness. And so we prove that it is unlikely that an adversary can do that. Recall that the construction in generate uses the outputs again as the input, that inner loop. So when you replace f with a random function, what happens is you have some input, some output, that's used again as the input, you get an output, that's used again as the input, and then if you happen to sample something that was already an input, that is a collision, and then the random function will cycle forever, and that is clearly not going to be ideal randomness, and that is the only bad event that can happen. Now, that was an intuitive overview of the proof. How did we actually formalize it? Our method uses Bellare and Rogaway's paradigm from 2008 of doing code-based game-playing proofs. So what this means is every game is actually written as a probabilistic program in a probabilistic programming language, and we use a Hoare-type logic to relate pairs of programs to prove them close or equivalent, and we use the identical until bad lemma, again from Bellare, to bound the distance between games. This is all done in a machine-checked manner in FCF and in Coq. So a quick overview of the proof tree. The goal of these slides is not to go over all the text, but to just give a flavor of the structure. So gray denotes every program equivalence proof. The interesting part here is that many program equivalence proofs in the crypto literature are not even stated, let alone rigorously proved. And doing things in a machine-checked manner requires you to rigorously state and prove all of them. So the majority of the work is done in bounding the difference between adjacent hybrids, and that expands as follows. Notice that there are a lot of program equivalence proofs involved, and that's what's being left implicit in the literature. Now, how do we verify the correctness of the mbedTLS C program? For brevity, we are not going to discuss the full API. That is this second arrow here, the proof of functional correctness. How do we do that? So first, let's discuss a toy example, proofs about functions in Coq and how they work. So first off, Galena, what these programs are written in, is an ML-like language that is also the expression language of Coq's logic. And you can use the logic to prove correctness properties of Galena functions. For example, a map just applies a function to every element of a list, and cat concatenates two lists. And it can state a theorem in Coq that says that map distributes over concatenating a list. Then you can write a proof script, each step of which is checked by the Coq kernel. Of course, this is a trivial theorem, and a more interesting one is that the HMAC-DRBG algorithm expressed as a function in Galena produces cryptographically strong pseudorandom output, which is the one we actually proved and discussed. Now, going to proofs about C programs, again, a toy example, but one that exemplifies what we did, is that this says, first we have the C language function that concatenates two lists, and the bottom specification is written in the verifiable C, and it says that the C language concatenate function takes two struct pointer arguments, underscore p, underscore q, whose initial values are p and q, and these point to lists in memory that represent the sequences sigma 1 and sigma 2. It says that catenate accesses only that memory. That's what the spec is saying. And it transforms the memory such that it returns a pointer value v that represents the concatenation of these sequences, sigma 1 and sigma 2. So notice that the specification mentions our functional specification of what catenate should actually do. So this is sort of how it works. The concatenate C program satisfies this functional spec, which we saw on an earlier slide. Right, so that concatenate function. And the verifiable C soundness property, which has also been proved as a theorem in Coq, is that for any derivation that a C program satisfies a verifiable C specification, if you compile that program using CompCert, which is a verified compiler, and run it, then its observable behavior will conform to that specification. So with respect to HMAC, this is what the actual HMAC functional spec looks like, just the core for simplicity, and you can find it at these URLs. Now, this is what the functional spec of the generate function actually looks like in Coq. So some types preamble, and then a recursive call that takes the output and uses it again as the input, just as I said. And notice that it actually calls the HMAC functional specification, which is a totally separate machine check proof. So these are actually being stitched together at this interface. This is what the HMAC API in C looks like. So key input, message digest input. And here's the API specification of HMAC. So some logical variables, propositions on them, precondition, variable bindings, memory predicates, postcondition. And then notice again that HMAC's functional specification is mentioned here. And we do have a similar spec for HMAC-DRBG, but it wouldn't fit on the slide. So again, BST actually guarantees memory safety. So there would be no buffer overruns, no reading from unspecified locations or writing to them. In conclusion, our work presents the first end-to-end formal security and correctness verification of a real-world PRG. The security and correctness properties flow from these theorems stated in Coq to a real implementation and can be composed with a verified compiler. Our proofs are modular, so you don't have to, anytime you want to do a new thing, you don't have to redo the entire line. You can rely on an interface that we have specified. So here's one open problem that we discovered. When we were doing this proof, we actually realized that we could only prove the security of instantiate if HMAC were an entropy extractor. And this is due to the design in NIST, where the entropy is given to a PRF's input rather than its key. It's actually not known whether HMAC is an entropy extractor the way that HMAC-DRBG uses it. So our attempt to verify it turned up this problem. And our actual proof uses an idealized instantiate, assuming that its output is ideally random. In terms of future work, we would like to prove more security properties of PRGs, such as backtracking resistance and prediction resistance. Here are two of the lessons we learned. Some of the NIST design decisions either made our proof harder or easier or just more annoying. So you already saw the ugly part, where it was the PRF was rekeyed in an inconvenient location in update. So we had to do some footwork there. A good thing that NIST did was, which I didn't mention earlier, was to rekey the PRF using a length extended input, so we knew that there would be no collision. And a bad thing, which we saw on the previous slide, was that the entropy is really put in the wrong place for PRF. And in general, verification helped us greatly with dealing with the tricky indices in the hybrid argument and with typos. We actually made several typos in the functional specification, and we just couldn't prove it correct until we caught those typos. Two more lessons learned. So part of the reason the recent crack attack happened was that, one, the specification was written on paper, so it wasn't really clear what implementers should have been doing. And two, there was actually a formal proof of several aspects of the protocol, but they weren't stitched together at the interfaces like ours were. So we think that an approach like ours could have helped mitigate it. And in general, we hope that our work will inspire NIST or other standards bodies to give formal specifications, at least of their primitives, not just paper pseudocode, and maybe even attach computer check proofs to them. And if you don't believe us, you can check out the artifact. It's on GitHub. It's open source. Thanks. Yeah, dual EC. Okay. Yeah, so comment on dual EC. One of our co-authors actually, as part of his thesis, tried to verify dual EC. I mean, he already knew it would fail, but then it failed, but and in an instructive manner that sort of pointed to the problems with this curve parameter. So, right, so that has already been done by one of our co-authors in his thesis. But yeah, you could definitely extend this work to other PRGs.
So my impression was that the previous HMAC paper was looking at the OpenSSL version of HMAC.
Yes.
Is that right? So when you were using HMAC here, did you re-verify the mbedTLS version, or did you?
No, we called out to the OpenSSL HMAC.
Okay, so
We did have to make a slight modification to do that.